Welcome back to our ongoing exploration of audio amplifier circuits. Let's begin by looking at the circuit we developed last time, which was a single transistor common emitter amplifier. I'm showing it now, and I'm calling it stage 1 because we're going to develop here a two-stage common emitter amplifier. Now the amplifier I have here is almost identical to the one I showed you last time. If you look at it carefully, you'll see the only difference, it's configured exactly the same way, the only difference is the resistors have larger values. And that's because this is the very first stage of an amplifier that's going to end up at the far end powering a loudspeaker, but that's to come by the end of the lecture. And this particular stage doesn't need to handle much power, and so we don't need very large currents flowing in it. So there's stage 1 of what's going to be a two-stage common emitter amplifier. Stage 1. Well, the idea that there's stage 1 suggests there's stage 2. Stage 2 looks identical in configuration, almost. I don't have an input here yet. And notice the resistor values are all considerably lower. They're lower because there are bigger currents flowing in this stage. Now, both of these common emitter amplifiers are what we'd call voltage amplifiers. Their primary purpose is to take an input voltage and make it bigger. Now, in the process, they also make the power available bigger, but their primary function is to amplify voltages. Get them up so they're out of the level where there might be subject to electrical noise. Get them big enough to feed into a real power amplifier that can deliver power to a loudspeaker. So it's a two-stage amplifier at this point. Each of them is connected to a 10-volt power supply, and we could connect them to exactly the same power supply, although if we were really sophisticated, we might isolate the power supplies slightly so that a heavy current flow in the stage 2 amplifier doesn't lower the voltage to the stage 1 amplifier. A lot of sophisticated things if you were designing a real amplifier that we aren't doing here. Now the question is, how are we going to join them? I can't just take a wire from the output of the stage 1 amplifier to the input of the stage 2 amplifier. And the reason I can't do that, remember we have this operating point established. For both these amplifiers, if I've picked the resistors right, it ought to be about 5 volts. So that output ought to be sitting at 5 volts when there's no input, and it ought to swing maybe 1 or 2 volts above 5 volts and 1 or 2 volts below 5 volts. More than that, and we're likely to have distortion. So we want to capture those swings in the output of stage 1, but we don't want to capture the 5 volt steady operating point level. Well, what device will let us do that? What device will let us do that is the device that blocks direct current, doesn't let DC through, doesn't let zero frequency through, but lets variations through, and that is, of course, a capacitor. So we're going to couple these two circuits with a capacitor. I put a 1 microfarad capacitor, which is good enough for audio work probably in this situation. Maybe it'd have to be a little bigger if we wanted to get to really bass frequencies because they're changing rather slowly. But there is now our coupled amplifier, and I've joined the 2 power supply connections to 1 power supply. In this case, probably not the best practice, but it will do for us. So they're now coupled, and I have a two-stage common emitter amplifier. Let's look at what this amplifier does, and let's add one more modification to this amplifier. I mentioned in the previous lecture that those resistors from the emitters to ground have multiple functions. They help stabilize the transistor against thermal runaway and things like that, but they also establish a gain that's independent of the beta of the transistor to some extent. So they mean you can take arbitrary transistors off the shelf and put them in basically the same circuit and they'll work the same. But as we saw last time, we had started with a gain that was of 150 or something. When we put that resistor in, that gain dropped to about 20. So we kind of lost gain. Well, you can get some of that gain back. You can gain back some of that gain by putting capacitors, because again, the capacitors are like the resistors for the AC, for the audio frequency voltage variations. And so they'll act as lower resistances, and since the gain is the load resistor over that emitter resistor, there'll be a higher gain for those time-varying signals that we're interested in. So this helps boost the gain. So that's why those capacitors are there. So let's now see how this device works. Well, again, I'm not going to wire up the whole thing on my board, but I wired it up in Circuit Lab. And by the way, if you would like to pause right now and do this in Circuit Lab, if you're planning to do the project, or Circuit Lab or Do Circuits, if you're planning to do the project for this particular lecture, this is going to be the first part of it, but you're going to have to do more. So if you want to explore the circuit right now, you could press pause, do that, and come back, and we'll look at the output. Well, here's the output from my Circuit Lab simulation of the two-stage common emitter amplifier. You can see that the voltage is swinging about roughly 5 volts. That's my operating point. Came out 5.1 volts in this case, close enough to the middle between the 0 and the 10. My two-stage common emitter amplifier. The swing is from the 0 level up to about 1.7 volts above it. So we're going from about 5.1 volts to 6.8 volts. But the important thing is that swing. That's the amplitude of the output variations. So we've got an output amplitude of 1.7 volts. We've got an input amplitude. I set that input voltage to 0.01 volts peak. And so we've got a gain, and I'm putting the absolute value sign around it because we've got to think about the sign. We've got a gain whose magnitude is 170. So the input voltage variations going through this two-stage common emitter amplifier have been boosted by this factor of 170. Well, that's about what we had with our first one-stage amplifier, but we didn't have that emitter resistor in there that stabilizes things and makes the gain basically independent of the individual characteristics of the transistor. So with two transistors, we've got back that high gain, but we have a much more stable circuit, and it doesn't depend on what particular individual transistor we put in it. So there is our two-stage amplifier. Well, I cautioned you last time we got to take into account the sign of the gain. Is the gain positive or is the gain negative? Is it a non-inverting amplifier or is it an inverting amplifier? So let's look now at the input and the output graphs from Circuit Lab. We would see the same things on an oscilloscope if we had a real circuit here. And this now is a non-inverting amplifier. Why is it non-inverting? Because we started and went through one common emitter amplifier, which we know from the previous lecture inverts. Turns the sine wave upside down. When the input goes high, the output goes low. And now that output that's going low is fed into the second stage. When the output of the first stage goes low, the output of the second stage goes high, and that's when the input of the first stage went high. So it's a double negation. It's -1 times -1. It's two negatives make a positive. This has a positive gain, and in this case, the gain is 170. So we've built a two-stage common emitter amplifier here with a gain of 170. Now, this amplifier is missing something we would probably like to have, and that's a volume control. We might also want to have tone controls, bass and treble controls. We already know how to make those. We would make those with filters, and we could insert those filters at various points in the circuit, but it'd be awfully nice to have a volume control. By the way, what we have here is what would probably in the old days be called a preamplifier. And you might have actually, in a stereo system of the 1960s or 70s or even 80s, you might have bought a separate preamplifier and then a power amplifier, and the volume control probably would have been in the preamplifier. So how do we add a volume control? Well, let me show you a device that we're going to use to add a volume control. Here I have a device which is called a potentiometer. Now, don't worry, you're not going to see a big clunky thing like this with a ceramic base and all this heavy-duty stuff in an audio amplifier. This is an ancient and very heavy and very power handling capability potentiometer. What's a potentiometer? Well, a potentiometer is another kind of resistor. What kind of resistor is it? Well, it's basically a resistor, and what we have here, in fact, is coils of wire wound around a piece of ceramic, and they start here, and they go all around here. And the resistance in this particular case just happens to be 100 ohms. So between this terminal and this terminal is just a 100 ohm resistor. But what we also have is a middle terminal, and that middle terminal connects through this mechanism to this adjustable slider. And that slider can move. And so it contacts different parts of this resistance. So right now it's in the middle. And so the resistance from here to here is 50 ohms, half of the total resistance, or from here to here. And the resistance from here to here is 50 ohms. So what I've got is a voltage divider, which if I put a voltage across these two outer terminals, I will get half that voltage at the middle. On the other hand, if I put, say, plus 10 volts here and 0 volts here, now I'll have 5 volts in the middle. If I crank all the way over to here, so it's connected to the 10, I'll have 10 volts. And if I crank all the way down to here, I'll have 0 volts. And so what this potentiometer allows me to do, it's a variable voltage divider. It allows me to divide the voltage as I choose by turning what you would see as the user, this knob, which turns that variable piece. So it's a little bit more than a variable resistor. A variable resistor would have two terminals and a knob, and if you turn the knob, you would change the resistance. This does something more than that. It taps off a fraction of the voltage that's applied across the whole thing. And by the way, if you wanted to have just a plain variable resistor, you could make it by taking the resistance across either pair of terminals with the middle, this pair or this pair, and you'd get the resistance between the first point and the middle point, and that would vary as you turn the slider. So that's a potentiometer, and one of its many uses is to be a volume control in an audio amplifier. In the old days, a big powerful one like this might have been used for something like controlling the brightness of a light bulb. But we know that's a horribly inefficient thing to do nowadays because most of the power would be dissipated as heat in this resistor, and we have far better electronic ways to handle that problem. I mentioned that that's not what you would find for a volume control in an amplifier. Well, a volume control probably in an older amplifier or one of those tube radios I showed you might look like this. And it's a similar thing. You just can't see it because the variable or the resistance is hidden behind this metal case. But you do see the three terminals, the two that mark the end of the resistance and the one in the middle. And so what we have if we want to add a volume control to our amplifier is a potentiometer, and I've placed the potentiometer in this case at the output of the first amplifier and before the input to the second stage. Now I've got to be a little bit careful in doing this. I'm introducing a new resistor into the circuit that wasn't there. And that's going to mess up the biasing and the operating point of the stage 1 amplifier unless that potentiometer has a much, much bigger resistance than that 10 kilo ohm resistor that I've got as the load resistance in my stage 1. So I might need 100 kilo ohms, 200 kilo ohms. That's getting awfully big. So if I were redoing this amplifier, I might actually put the volume control at the output of the second stage, because then the potentiometer resistance would only need to be much bigger than the 500 ohm load resistance in that case. But it doesn't really matter. The idea is here. As I slide that slider up and down, and you can see the symbol for the potentiometer, it's a resistor, and then it's got this little pointy arrow which represents the slider that you can imagine moving up and down along that resistance. If I move it all the way up, I get the most volume I can have. I get the full output of stage 1. If I move it all the way down to the ground, I get 0, and even though stage 1 is producing an output, there's no input to stage 2. So that is our volume control. Now, so far, we have a nice two-stage common emitter voltage amplifier. We've increased the gain by putting those capacitors across the emitter resistors. We've added a volume control. Pretty good. The problem, though, with this and many other amplifiers is, in this configuration, even if there's no input to these amplifiers, there is still current flowing through their load resistors and through the transistors because we're trying to hold that operating point about halfway between, in this case, the 10-volt supply voltage and the 0 volts of ground. And that means we're dissipating power in the load resistors, and we're dissipating power in the transistors, and we're wasting energy. Now, at the early stages of an amplifier, that's not a problem because it's not a lot of power. But when you build a 200-watt audio amplifier, you would really like it when the music is quiet for that thing not to be drawing much power out of the power line. And if you simply continued with bigger and bigger power versions of this common emitter amplifier, you would be dissipating hundreds of watts, even when the thing was completely quiet. And you don't want that. That's a crazy waste of power, contributing to climate change, doing all kinds of bad stuff that you don't want to do, and wasting your electric bill, and heating up the amplifier, and making the components wear, and all kinds of bad things. So we need to develop a power amplifier that can handle lots of power and drive a loudspeaker for an audio amplifier, but that won't dissipate power when things are quiet. And that circuit is called an emitter follower. Well, not quite. The emitter follower is going to be part of that circuit. The emitter follower is a current amplifier. It's also called a common collector configuration because you'll notice that the collector of the transistor is connected directly to the power supply, which, along with ground, is another common point in the circuit shared by everything. And so this is a common collector, not a common emitter, but a common collector amplifier, also called an emitter follower. Why is it called an emitter follower? Because we take the output at the emitter, and the output basically follows the input. So what happens is we have a voltage gain, which is basically 1. It's actually a little bit less than 1 if we're dealing with small voltages because of that 0.7 volt drop across the base to emitter junction. So this amplifier does not have, it has no, well, I don't want to say it has no voltage gain. It doesn't have 0 voltage gain. It has a voltage gain of 1. It doesn't gain you anything in voltage. It passes the input voltage through as an output voltage. But what it does do is amplify current. So there comes a small base current in. Down comes a much bigger collector current, beta times the base current, beta being the current gain of the transistor. Both of those combine and go through the emitter resistor, and the output voltage is approximately the input voltage minus the 0.7 volts at that junction, but there's a lot more current. So this is a current amplifier, and because it's amplified current, there's also a lot more power available to pass through that load resistance than there would have been coming into the input. So it is a power amplifier. So were our voltage amplifiers, but this one is amplifying power by amplifying current. And you could replace that load resistor by a loudspeaker if you wanted to. So there is the emitter follower, a current amplifier, a power output stage, sort of, for big power amplifiers. But so far, it's still not all that good. Let's just take a quick look at it. The current gain of this thing is I through the load. The load is now in the emitter lead, so it's carrying both the emitter current and the base current, so it's beta plus 1. Beta for the current coming through the collector. Remember, beta is about 100 or so. 1 for the extra current coming in through the base. Beta plus 1 is close enough to beta because beta is on the order of 100. Who cares whether it's 100 or 101 or 99 or 150 or 151? Doesn't matter. So it's essentially approximately beta. The problem with this amplifier is it too, when we're in the quiescent state, has to be biased or that transistor will turn off when the input voltage goes negative. And we therefore are going to have to bias this one just like we did the other amplifier or in some similar scheme, and we're going to be dissipating a lot of power when things are quiet. And that now matters because that resistor, if it's a loudspeaker, typically has 8 ohms of resistance. It's very low. Lots of current is going to flow. There's going to be significant voltage. The power supply voltage for a big power amplifier might be 30 or 40 volts, maybe even more. A lot of power. We don't like that. We're wasting energy. We're heating up that load resistor. We don't need to. So what can we do that would make this better? Well, remember when we talked about semiconductors, I mentioned that we have, of course, the beauty of semiconductors is we have these 2 kinds of semiconductors, p-doped and n-doped, p-type and n-type. They're complementary. One has positive charge carriers, holes. The other has negative charge carriers, electrons. And we've been dealing almost exclusively since then with NPN bipolar junction transistors. But I pointed out when I introduced transistors that we could equally well make a PNP bipolar junction transistor, which is complementary. And what we're going to do now is develop a complete output amplifier stage, the final stage that's going to drive the speaker, and we're going to make use of that complementarity of the 2 transistors. We're going to develop a circuit called complementary symmetry. Now, I'm going to show you the simplest rendition of complementary symmetry. I should point out that if you look at circuits for real amplifiers, there are in fact asymmetries between the workings of PNP and NPN transistors, and they have to do with the different ability of holes and electrons to move and carry current. And so sometimes you will see circuits that you'll scratch your head about. Looks like they have 2 NPN transistors, but they're actually simulating a PNP transistor with an NPN. The circuit I'm going to show you is going to be truly complementary and use one NPN transistor and one PNP transistor. So how does this work? Here is our basic emitter follower amplifier. Now, I'm first going to take that load resistance and move it so it goes out to the right. It's the same circuit. You remember, you can draw a circuit any way you want as long as you got the connections right. So that is the same circuit I just showed you. Just got the load resistor going off to the right. And now I'm going to bring in a PNP transistor, and I'm going to connect its collector not to ground, but to a negative supply voltage. So maybe I've got plus 10 volts at the top of the collector of the NPN transistor, and I've got minus 10 volts at the collector of the PNP transistor. And you'll notice I've connected their 2 bases together. And just to emphasize that word symmetry, I'm going to redraw it with the base, the input connection to the middle. So now this thing is completely symmetric. Draw a horizontal line through it, especially if I had run that ground connection sideways, we'd have perfect symmetry. And we do have perfect symmetry electrically. We got an NPN transistor on the top, a PNP transistor on the bottom, positive power supply at the top, negative power supply, again, relative to ground. So the collector of the lower transistor is 10 volts, say, below ground. The one at the top is 10 volts above ground. If we're talking 10 volts, there's 20 volts between the V plus supply and the minus supply. And now, how are we going to get an input into this thing? Well, let's take a look at what we've got with our load line analysis. So there's the load line analysis we did in the previous lecture for an NPN transistor. We have this load voltage, we have the load current. They have to lie somewhere along that diagonal line, the load line. They also have to lie somewhere along those characteristic curves, the transistor curves. And I pointed out when I first drew these for a transistor, transistors only work in one direction, so we don't draw all four quadrants. But now we have two transistors. There's cutoff and saturation for the NPN transistor, but we also have the PNP transistor with its own load line and its own saturation and cutoff. And what's the idea behind this complementary symmetry amplifier? Here's how it works. Suppose Vin is 0. Well, if Vin is 0, then both transistors are at cutoff. There's no current flowing anywhere, and Vout is 0. But what if Vin is greater than 0? If Vin is greater than 0, we get some current flowing in through the input lead, through the base emitter junction, because that's going to be forward biased, out through the load resistor and to ground if Vin is 0. And that means the upper transistor, the NPN transistor, is conducting, it's working, it's transisting, it's being a transistor. And we get a bigger collector current, and the collector current flows through the load resistance and to ground, and we've got amplification. But that's only going to work if Vin is greater than 0. In fact, this is what was wrong. This looks like the common emitter amplifier I started with as our first try, and I said it doesn't work. And it didn't work because if the input went negative, the base emitter diode was shut off and the thing didn't pass any current, nothing happened. But now we have that second transistor. And so what happens if Vin is less than 0? Well, if Vin is less than 0, everything goes the opposite way. We get a small current flowing in from ground, if you will, through the load resistor and in through the base emitter junction, which is forward biased now going to the left. In other words, if we put a negative V in, we draw a little bit of base current like that, and that causes a much bigger collector current. And again, the collector current goes the other way because it's a PNP transistor. And now we get current flowing from right to left, a big current flowing from right to left in the load resistor. So the beauty of this thing is it will amplify when the input signal goes positive by turning on the NPN transistor. And it will amplify when the input signal goes negative by turning on the PNP transistor. That's why it's complementary. We have these two complementary transistors, and they complement each other. One of them amplifies the positive going half of the cycle, and the other amplifies the negative going half of the cycle. Beautiful. And the beauty of it is when there is no input, when the input is 0, neither transistor is on, we're dissipating no power. We only draw power when the cymbals crash, and a lot of current has to flow. When the music is quiet, no power. Great, it solved our power problem. However, it's got another subtle problem. And here's the subtle problem. I did a simulation of this circuit in Circuit Lab to show you. It's got an 8 ohm load. I've got a Vout labeled. I got 10 volts there at the NPN transistor, minus 10 at the bottom. I've got an input sine wave coming in. And I'm showing you pictures of V in and V out. They're not identical for two reasons. One is V out is actually a little bit less than V in. There's a number of factors there. These transistors you're using in these simulations are in some sense like real transistors. They got some aspects that we've been ignoring. Part of the reason for that. The other part of the reason is there's that 0.7 of a volt drop across the diode. And that 0.7 of a volt drop across the diode leads to the other problem. Look at that Vout graph, the lower graph. You see we get a nice rising sine wave, but then we get this little flat part. Uh-oh. And then we go down to the negative half as the lower transistor, the PNP transistor, kicks in and starts amplifying. But there's that little short time when it's 0. Why? And why don't we want that? Well, let me tell you first why we don't want that, and then I'll tell you why it occurs. Here's why we don't want that. I'm going to play you a sound that is basically 2 seconds of what the output of this amplifier sounds like, followed by 2 seconds of, actually it's going to start the other way, it's going to be 2 seconds of pure 440 hertz A above middle C tone, as it should be, as the input would sound, for example, in this case. And then I'm going to play 2 seconds of the output, and it's going to repeat that. So you will be able to hear the difference between what the input signal sounds like and what the output signal sounds like. So take a listen. And I think you'll agree that the distortion is plainly evident in that case. This is not high fidelity. High fidelity means faithfully reproduce. Fidelity, faithfully reproduce the input. We are not faithfully reproducing the input, and it's because of that little glitch that occurs. Now, why does that glitch occur? It occurs because what does it take to turn on the NPN transistor? It doesn't take a voltage going positive. It takes a voltage going above that 0.7 volts that it takes to turn on the diode. And what does it take to turn on the PNP transistor? It doesn't just take the input going negative, it takes the input going below that 0.7 volts, so when the PNP transistor will turn on and current will flow from right to left through it. Problem. And so that little glitch is caused by the transistors turning off during that interval when the input voltage is between plus 0.7 volts and minus 0.7 volts. Neither transistor conducts, and the output therefore is 0. That's called crossover distortion. It's occurring when we cross over from the upper transistor conducting to the lower transistor conducting. And by the way, you'll notice I've got a 2N3904, that's the designation of a transistor, and a 2N3906. There are transistors that are made to be basically matched complementary pairs, one NPN, one PNP, and the 2N3904 and 3906 are such a pair. So what do we do about this crossover distortion? How do we get rid of the crossover distortion? Well, there's an easy trick. So our trick for getting rid of the crossover distortion is to simply put a couple of diodes running in a string with resistors in series with them, nice and symmetrically, from the plus 10 volts down to the minus 10 volts. And so there's going to be current coming down through that string of resistor and diode. Both diodes are forward biased. Current is flowing down through that string, and both diodes therefore have 0.7 volts across them. The input is coming to the gap between the two diodes, and what the diodes effectively do is they take the base of the upper transistor, the NPN transistor, and they make it 0.7 volts positive. So it's just on the verge of turning on. And the lower diode takes the base of the bottom transistor, the PNP one, and it makes it 0.7 volts below ground, and therefore just on the verge of turning on that one. And so now, if the input signal swings even the slightest bit positive, bingo, the upper transistor's on. If the input swings even the slightest bit negative, the lower transistor goes on, and we have no crossover distortion, and the graphs of the input and output show that these things are identical. What a great and elegant solution to that problem relating to that internal, ultimately that internal electric field of the PN junction. Okay, well, I could stop there, but I'm not going to. I want to say one other thing. I'm going to now give you a mantra, which I'm going to be repeating from now till the end of the course. It's a very strange mantra for someone who wants you to learn electronics and build electronics. And the mantra is, well, let me tell you the mantra. The mantra is don't build, buy, or buy, don't build. Because nobody today would go out and build an audio amplifier from scratch, unless you want to do it as kind of a learning process. You would go out and buy an integrated circuit audio amplifier. And I'm going to just show you in the last few minutes what one sounds like. So what I have over here, let me turn on the oscilloscope on the big screen so you can see it. What I have over here is a so-called LM386 integrated circuit audio amplifier. It's got 10 transistors in it, 7 resistors, and a couple of diodes, not surprisingly. It has a kind of complementary symmetry output, although, as I mentioned, it fakes it with NPN transistors. It's all on that little chip, everything. I'm coupling it out to a loudspeaker that's built into my little breadboard here, and we are going to listen to the output of that loudspeaker once I turn it on. And there's the music. And once again, the music is my sister's hammered dulcimer playing. And if you want to know what the music looks like, if you've ever wondered what music looks like, there it is on the oscilloscope screen. That's the input, so when I turn off the amplifier, it doesn't turn off. Now that's a cute little amplifier, costs a few cents, maybe a few tens of cents to buy one of those chips. It can produce up to a watt of power, not a huge amount, but significant for many applications. If that's not beefy enough for you, well, go to this one, don't build, buy it. This is an LM3886 integrated circuit audio amplifier, and it can produce 68 watts continuously, 134 watts in peaks, and it costs about $10. It's used in high-end televisions, stereo systems, and others, and it's basically a complete audio amplifier. You hang a few more components, resistors and capacitors, on the outside of both of these to give them the gain you want and some other features, but basically they're audio amplifiers all in themselves, but they work on the principles we've just learned here. So that's the end of this lecture. If you want to do the project, you're going to build your own complete audio amplifier. Okay, your project here is to simulate the combination of a two-stage common emitter amplifier. So if you did the previous project, you already built one stage of that. And maybe if you did the lab part of this lecture, during the lecture, you've already got part of that done. And then combine it with a diode-biased complementary symmetry output stage to make a complete audio amplifier. Remember that diode biasing was to take out that crossover distortion. So use the two-stage CE amplifier earlier in this lecture, which you may have built. Use the complementary symmetry amplifier that I just introduced. Couple them with 1 microfarad capacitors. And for the input, use a 25 millivolt 1 kilohertz sine wave. Find the voltage gain and calculate the power delivered to the load. Okay, well, here is what my circuit looks like in Circuit Lab. It's basically the circuit I showed you in the lecture. It's basically the two circuits. Now they've been coupled with that coupling capacitor between the CE amplifier, which itself has a coupling capacitor between its two stages. And there we are with the diodes that bias to prevent that crossover distortion, and so on. And so we're supposed to find the voltage gain and calculate the power delivered to the load. So let's simulate this circuit. And we'll run a time domain simulation. And there we are. Okay, so we are looking at a voltage swing of something on the order of going from 0 volts up to about 1.5 volts or 1.7 volts maybe, and down to about minus 1.7 volts at the output. So a swing of 3.4 volts at the output, and the swing at the input is 50 millivolts from plus 25 down to minus 25. So 50 millivolts to 3.4 volts. Let's try to figure that out. If it was 100 millivolts, it would be a gain of 10 to get to 1 volt, a gain of 34 to get to 3.4 volts, and so it's twice that because it's only 50 millivolts. That's a gain of about 68. So there's the gain, and let's go through that calculation a little more carefully. Here's the calculation. The gain is about 1.7 volts over 0.025 volts. Those are the peak amplitudes, and that is the 68 I just calculated in my head. And the power to RL, well, power is V squared over R for a resistor with a known voltage across it, and you work that out. It comes out 360 milliwatts. That's doesn't sound like a whole lot. You probably have a 200 watt stereo amplifier or something, but it's actually significant audio power for most uses. Your cell phone, for example, probably produces about 30 milliwatts of audio power when it's on speakerphone. So this is 10 times that. So it's a reasonably significant power. Let's take a look at the same amplifier-induced circuits. I won't bother to go through the whole thing, but there it is. Looks the same. I've used batteries instead of, that has batteries for its DC power sources. I've used a function generator, nice function generator that we have available, a simulated instrument, induced circuits. And if I run it and run the time domain analysis, I get results that are similar, but they're not identical, and I'm not absolutely sure why they aren't. Perhaps the transistors have different specs or other things are wrong, but you can see clearly we've got the amplification. The input and output are approximately in phase, and we're looking pretty good. So there is a complete audio amplifier, and that really is a significant achievement to be able to build that much. A two-stage preamplifier, a complementary symmetry output stage, complete with those diodes for eliminating distortion. Good work building that amplifier.